topics of discussion, go through the topics of discussion. In order to give a better understanding of my view of the scrap industry, I will give a brief introduction to the ELG Utica Alloys Group. This is followed by the impact of using scrap, which will touch on both the environmental and logistical benefits of scrap incorporation and tie melting. We will then pivot to the scrap trends, following the factors in decision-making for utilizing scrap and the general idea of how it is valued. The impact of OEMs controlling their revert will illustrate the various factors considered when implementing a scrap return program. All of these decisions have a direct impact on the scrap processors, and I will offer my opinion on the role of scrap processors in today's market. Next, we will move into the more challenging questions of what happens with the scrap when these scrap flows change, and the impact of increasing revert melting outside of the US, specifically Europe and Japan. So an introduction to the ELG Utica Alloys Group. ELG is a world leader in state-of-the-art certified processing of both titanium superalloys, solids, and turnings. We have 11 locations in 6 countries dedicated to the processing of titanium superalloys, and another 34 facilities of the ELG Group in the US, Europe, and Asia, which are available to supplement our service and logistical solutions. Main processing units are in Sheffield, Lyon, and Duisburg in Europe, with Herkimer, Hartford, and Monroe, North Carolina in the US. ELG Utica Alloys' goal is to provide the greatest value to our customers in the titanium industry with a service-based approach, focusing on improving technology in order to reduce costs and growing our relationships so that we can be a one-stop global solution to our business partners. Putting aside the financial benefit for the moment, I'd like to focus on the environmental impacts of using scrap. In terms of both energy consumption and CO2 emissions, the reductions are truly impressive, with greater than 95%. The types of scrap that are utilized are defined by the melting technology a company has. VARs prefer bulk weldable, with limited capability to consume feedstock and turnings. Exceptions are strictly controlled, with pedigree and X-ray technology. Cold hearth melting, both EBs and plasma have been designed to consume feedstock and turnings, and generally not as efficient as consuming bulk weldable. Unfortunately, many of the scrap return programs create scenarios where melters are receiving materials that are either inefficient or unusable for their melting processes. I will touch on this a little later in my presentation. Scrap trends. Vacuum quality scrap is traditionally capped by sponge on the top end and buffered by ferrite steel consumption on the bottom end. When looking at the scrap market, it would be easy and self-serving to reach back into the mid-2000s to show slides that have a much greater range than the one shown here. That is not today's reality, one which has overcapacity of sponge production, as mentioned by Sylvain, with more planned to come online in the next few years. We start with the lows of the financial crisis in 2009, followed by a scrap shortage due to lack of machining and an immediate ramp up of melting in 2010. In 2011, the unfortunate events of the earthquake and subsequent tsunami forced the shutdown of the Fukushima Daiichi power plant, creating uncertainty in the ability of the world's largest aerospace sponge producers to fulfill orders. The following decrease was a result of increasing scrap generation, which followed through 2012 and 13. Increasing melt rates in 2014 brought about volatility that continued in the second half of 2015. When the increased availability of sponge, the integration of 2 of the largest tie melters in the world resulted in a renewed focus on inventory reduction. This trend, along with the complete erosion of the ferrite market beginning in 2014, has left tie scrap at values not seen since 2013. Along with normal economic factors of lower steel prices, ferrite has been impacted by a consistent supply of scrap from aerospace industry. This may seem like a positive ramification, but it has greatly contributed to lower ferrite scrap prices, along with increased competition and economic uncertainty. More immediate trends in 2017 suggest a recovery in both vacuum and ferrite pricing. With regards to the availability of scrap, there are several key factors. 1, buy-to-fly ratio, noting scrap generation. 2, ingot mill product processing, which I can't calculate. Ingot production, and 4, scrap incorporation rates. Here are 2 examples. In one, showing a negative 3.5% deficit in aero scrap using 8-to-1 buy-to-fly ratios, an assumption of 40% ferrite scrap rate, and 56% scrap consumption results in a negative scrap availability of almost 2,200 tons. Making slight changes, ferrite ratio from 40 to 30%, meaning more vacuum quality scrap available. We would need an 11.3% increase in ingot production in order to consume this scrap. And change scrap incorporation rate to 70%, and you will see almost a 10,000 ton shortfall, or 17.5%. This slide will give a better visual representation of a specific scenario, assuming 61,800 metric tons of tie ingot production, an 8-to-1 buy-to-fly ratio, and a 60% of scrap generated as vac quality. At 50% scrap incorporation, there's 1,500 metric tons of excess scrap. At 57.5% scrap incorporation rate, there's a negative 3,000 ton deficit. And at 65%, a 7,700 ton deficit. The industry is correctly focused on reducing buy-to-fly ratios in an effort to reduce the cost of titanium. One drawback is that the scrap that is generated tends to be smaller. When specifically looking at turnings, the major component of scrap generation, the lighter the cut, the higher the oxygen. This limits scrap incorporation rates. Heavy cut chip generated with higher buy-to-fly ratios can be consumed at a rate of up to 25% more than chip generated with a finish or light cut chip. This is an important calculation that requires some intense review by OEMs, melters, and scrap processors. While reducing buy-to-fly ratios is the right thing to do, there must be a recognition that all scrap is not created equal, and thereby the value will be a more complex transaction in the future. Impact of OEMs controlling the revert. Scrap return programs, while not unique to the titanium industry, they were certainly much more essential due to the fact that unlike other industries, aluminum and nickel, titanium has no terminal markets like the LME to reduce risk. In this vein, they were designed to reduce the market impact on mill product and scrap pricing, reducing the trading aspect of the business, which lent itself to speculation. Initially, OEMs found as a way to reduce their mill product costs with a specific melter, but as the industry has matured and the values become better understood, they are finding it more advantageous to control it themselves. As you can see in this slide, the flow of scrap is anything but simple. There are at times up to 5 companies touching the same piece of metal with a percentage of scrap that is owed to a melter, or in some cases, multiple melters. Initially, the programs were US-based, or the scrap was generated by the OEM directly. Supply chains have become much more complex, offshoring and reshoring, forging and machining operations spread from historic aerospace clusters to the far reaches of the industrialized world and sometimes beyond. These changes necessitate greater control, organization of scrap streams by the OEMs, melters, and perhaps a changing role of the scrap processors in today's market. So, there we go. A traditional look at the processor's role would be to focus on trading, toll processing of major alloys, Ti-64 and CP, and possibly items such as titanium alloys that are typically low in scrap percentage consumption. These alloys, such as 6242 and 1023, amongst others, have lower scrap incorporation rates due to OEM qualification requirements or a lack of scrap that meets vacuum-grade quality requirements. The processor's role is to develop suppliers and quality system that ensure these sensitive alloys will be usable as a vacuum scrap on a consistent basis. As we look at current and future role of scrap processors, we must first acknowledge that this industry has and must continue to mature in order to stay competitive. Apologize. Stay competitive. And our potential replacement materials. These are the demands of the customers, the OEMs. The scrap processors can choose to change, be forced to change, or risk being marginalized. Looking at this map of manufacturing clusters and melting capacities, one thing becomes clear. The industry, which was always small, now has no secrets. Large scrap generators will be tied up by OEMs, or in some cases, be purchased by the melters. This will necessitate that the scrap processors work to provide the infrastructure to manage these flows, shifting from trading to providing logistics and toll processing for the industry. It is clear that managing a revert cycle is not just a processing challenge, it's a logistical challenge, and even more so a data management challenge, something I briefly touched back at Scottsdale. Our industry has excelled at processing tie waste so it can return it to the revert stream. It now must come to the grips with logistical challenges supporting customers with operations around the world. To take this a step further, bring together the data surrounding processing and logistics. Data that we were able to see in the pipeline of metal around the world, we were able to match supply with demand, help our customers understand what the supply chain looks at, like not just 3 months in their melt schedules, but a year out with their demand planning. We are able to see where metal is arising, where quality issues are most likely to occur, and anticipate this, try and give complete transparency of where every pound of metal is, where it has been, and what processing has been performed on it. We can see what is conforming, what is non-conforming, and match it to the supplier of the material. Overall, this means we are able to get more metal back into the revert stream faster. Equally as important, giving a longer line of sight to raw material supplies, allowing greater confidence in raw material demand planning for our customers, as well as offering great value for money recycling. We can now and must develop this as a true value-added service. Scrap flows. Here we illustrate U.S. scrap consumption since 1995. From 1995 to 2015, the percentage was 48.5% and 46,000 metric tons. Parsing this a bit further, you see 1995 to 2008, signifying the end of the large industrial CP projects, was 41% and 52% in the years since, roughly a 25% increase. This is significant due to the fact that historically it's easier to include high percentages of scrap in CP melting. As CP melting decreased, the melters were able to increase the incorporation rate in tie 6-4 on their alloys. Why is that important? The titanium industry has, to this point, been able to build upon a platform that assumes that scrap must go to the U.S. for melting. That is supported by history, and I'll give you a few examples. From 2002 to 2006, the top importers are the UK at 37,000 metric tons, Japan 31,000 tons, Germany at 28,000 tons, France at 24,000 tons, and Korea at 7,500 tons. On average, from 2011 to 2015, the UK averaged 3,500 tons per year, Japan 2,300 tons, Germany 2,600 tons, France 2,000 tons, and Korea 1,100 tons. There are a few things to note. Japan averaged 2,200 tons from 2002 to 2008 versus 2,275 tons from 2011 to 16, while transitioning from exporting CP scrap to tie 6-4 and alloy scrap. This is the growth of machining operations in Japan to support the OEMs. In 2015, Japan exported over 3,300 tons of scrap, a direct result of the growing machining base and reach of the OEMs claiming their scrap. France averaged 22,000 tons per year from 2011 to 16 and 2,500 metric tons in 2015 alone. One can assume that over the coming decade, these scrap flows will be curtailed or diverted in their entirety to support regional melt facilities. An interesting parallel exists in the steel industry supported by ferritized scrap. As an industry, comparatively speaking, in 2014 to 15, steel production went down 2.9% as a result of declining oil and gas demand. Comparing 2015 to 2016, you see a 4.8% increase, which is seemingly stark. But when you remove 2015 and compare 2014 to 2016, it's only a 1.7% increase. There was destocking in 2015 throughout the supply chain in steel. And this is in line with expected growth of 1% for 2017 and 18. As we know, the growth is not evenly spread across all economies. India, Turkey, and Ukraine steel melting increased over 5%, along with a rebound in the US and the European markets has created a rebound in scrap pricing due to shifting demands and a shortage of available scrap in traditional markets. It is worth noting that the more established or traditional melting countries were essentially flat. Even China only grew at a 1.2% clip. While not the sole cause, it is a contributing factor to pricing coming off of historic lows. Much like us, the market is a creature of habit. Even a slight disruption or change in the status quo creates uncertainty and subsequently variability in both price and supply. Scrap melting outside of the U.S. Eco-Titanium, these are in France, is a joint venture will bring state-of-the-art melting facility to France, which will be capable and focused on consuming both internally and externally generated scrap. This will have a direct impact on the availability of titanium scrap for export to the U.S. Developments within Japan for both NSSMC and Corby, both companies have committed to qualifications for the aerospace industry. As noted earlier, there's increased volumes in scrap being generated of alloy, 6-4 alloy, and this could disrupt those flows to the U.S. as well. And Russia has continued to try and increase their scrap utilization, and through different programs with value-added agreements with both Airbus and Boeing means that traditionally scrap generations may be curtailed or not available to the Western world. In conclusion, as a result of one of the longest sustained cycles in the titanium industry, scrap generations will continue to support future melt volumes. Factors which could cause interruptions are new supply chains to support regional melting operations, an increasingly complex scrap return structure that stretches our logistics, and other new entrants into the supply chain. OEMs, melters, and scrap processors must continue to work together in order to ensure the supply chain reaches full maturity. This will decrease volatility in markets and grow our industry by guaranteeing consistent, stable supply and value to our customers. Thank you for your time and attention.